Next we have types of functions. We already know what a function is. Now we are going to classify functions into different types. Let us see these diagrams. These are arrow diagrams of some functions. You may be wondering why I drew all the diagrams on this side. That is because I am going to write something here and then we are going to need these diagrams. That is why. Okay, so don't get confused. Let us first focus on the upper left hand diagram, which is this thing. You see two sets here, x1 and x2. x1 and x2. x1 consists of 1, 2, 3 and 4 and x2 consists of these letters a, b, c, d, e and f. And the relation, let us not call f1 straight away a function. The relation f1 relates the elements of x1 to the elements of x2 in this way. 1 is related to a, 2 to b, 3 to d and 4 to c. And now is this relation a function? For it to be a function, each element in x1 has to be related to something in x2, which is true because each element has an arrow going out of it. And only one arrow should go out for each element. Or in another terminology, each element of x1 should be an input. And each input should have exactly one output. Yes, that is the case. 1 is an input and it has only A as its output, nothing else. The same can be said about 2, whose output is B, 3 has the corresponding output D and 4 has the output C. So yes, f1 is a function. Similarly, you can see the second one. Here also x1 is that x1 and x2 same. But this time the relation is f2 and it's like this. The input 1 has output B, 2 also has output B, 3 has output C and 4 has output D. Again, all the elements in x1 are inputs and each one has a single output. So f2 is a function, f1 is also a function. But now do you see one difference between f1 and f2? Obviously they are different functions, I am not talking about that difference. The difference in their types in the sense that in f2, two different inputs have the same output. But that's not the case in f1. If inputs are different in case of f1, outputs are also different. Or if you think of the arrows are going in a one-to-one manner. One here, one there, one here, one there, one-to-one manner. Not like this, which has a 2-to-1 nature, 2-to-1, or in general many to 1. So the functions which are like f1, they are called one-to-one functions or injective functions. You can see that aspect in the third and fourth one also. In this third one, again you can quickly check that f3 is also a function, but the state is different here. It's no longer x2, it is x3, which consists of a, b and c. And now the inputs 1 and 2 have the output A, 3 has the output B and 4 has the output C. So whatever we said just now about f1 and f2, you see that f3 is like f2. Here also two different inputs have a single output. It has that 2-to-1 nature. But this other one, f4, where this time again the set is different, it consists of, the second set, A, B, C and D. This one has the same nature as this one. Different inputs have different outputs. Oh, and one more thing. Obviously, a single input cannot have more than output. I mean, it can have, but then it's not a function. To remember all these things, you can think of a function as a kind of a border between two countries where soldiers from both sides are stationed and say one side is shooting. Okay. In this part, okay, or in this arrangement, the soldiers, of course, from this side are shooting the soldiers on that side, on that other side. And different soldiers are having different targets. Okay, so that is the one-to-one nature of this arrangement, or that is the one-to-one nature of this function. Here, however, we see that two soldiers of the same side are attacking a single soldier on that side. Maybe this is a very important target. So two are attacking simultaneously. The others, of course, have got their own targets. And you also see another aspect which I haven't talked about yet, is that some soldiers are surviving because they are not being attacked. We are coming to that later. Okay. That way also you can remember these things. But you do understand now, it's nothing very difficult to understand. 1 to 1, many to 1, 2 to 1, 3 to 1. So in all of these types of functions, that nature is not there. We do not further classify functions like 2 to 1 or 3 to 1. If this nature is not there, then we just simply say that the function is not 1 to 1. So that means f1 and f4 are 1 to 1 or injective functions. f2 and f3 are not 1 to 1. Let us now write the actual definition and see how it looks. So this is the definition. A function f from the set x to the set y is said to be 1 to 1. We can also write 1 dash 2 t or 2 dash 1. That way also we can write, or we can simply write 1 1. Sometimes we also say 1 1 instead of saying 1 to 1. So such a function is said to be 1 to 1 or injective if the images of distinct elements of x, like that one, under f are distinct. That means not like this one, where these two elements, although they are distinct, but their images are same, they are not distinct, not like that one. If distinct inputs have distinct outputs, then the function is 1 to 1. i.e., if for any inputs x1 and x2 in x, we have this implication that if x1 is different from x2, then f of x1 is different from f of x2. Now, in place of this condition, you can write another condition which is logically equivalent to this, which is this implication. If f of x1 is equal to f of x2, then that implies x1 is equal to x2. Why is this logically equivalent to this? Do you remember logically equivalent statements? Two statements are said to be logically equivalent if they are either simultaneously true or simultaneously false. In other words, if any one of them is true, then the other one also has to be true. And if any one of them is false, then the other one also has to be false. Recall from your, there was one chapter in the previous year where you came across these elementary logic things. a statement, its negation, if then statement, its contrapositive. Do you remember? An if then statement has the form P implies Q, or if P then Q. So this is a statement of that form, where P is this simple statement that x1 is not equal to x2, and Q is this simple statement that f of x1 is not equal to f of x2. And the implication is the compound statement P implies Q. What is its contrapositive? Contrapositive is negation of Q implies negation of P. The statements switch sides when you take contrapositive, and in place of the statements themselves, we consider their negation. That means if the original statement is like this, P implies Q, then its contrapositive is negation of Q implies negation of P. This is our Q. What is its negation? That f of x1 is equal to f of x2. What is the negation of P? That x1 is equal to x2. So that is why in place of this you can also write this. Essentially they mean the same thing. Essentially means essentially I say because they are also either both true or both false. Okay. Now what will you do if you encounter a function and say you are asked to prove that it is 1-to-1? You can use either this one or this one. No matter which one you use, if you can successfully show that the function is 1-to-1 using either one of them, it's okay. It's up to you. Sometimes it's convenient to use this one, sometimes we can use this one. In the text only this is given, but this one is also a legitimate condition. Okay, so that is the notion of a 1-to-1 or injective function. If a function is not 1-to-1, then it's called many-to-1, or like how you write this term 1-1, you write many-1. This is the many-to-1 function. This is the many-to-1 function. And next we come to that aspect where we see that some soldiers on the enemy side survived because they were not attacked. So the next point here is that in this first firing, there are some soldiers who were surviving, E and F. In the second firing, A, E and F survived. But the situations 3 and 4 are merciless. Everyone is eliminated on the side that is being attacked. And based on this observation, we are again going to classify functions into two types. Note that this condition of soldiers surviving or not surviving actually is independent of how many people are attacking a single soldier, which we used in classifying functions into the two types. One is 1-to-1 function and the other one is many-to-1 function. This condition is independent of that. So let's see the definition. Okay, so this is the definition. Again, a function f from the set x to the set y is said to be onto or surjective if every element of y is the image of some element of x under the function f. That is, if for every y belonging to y, there exists x belonging to x such that y is equal to f of x. In our analogy of a border and soldiers shooting each other, this means that a shootout is onto if every soldier from the side that is being attacked is being attacked by someone from the attacking side. That is, every soldier y in y is being attacked by some soldier x in x. If that's the case, then the function is onto, as opposed to this more restricted type of attack. Alright, now there is a third definition also, based on how we can also have a function that has both these properties, that is, it is 1 1 as well as onto. That type of functions is very important in mathematics. So this is the third definition. A function f from x to y is said to be bijective. The one that also is called injective, an onto function is also called surjective, and a function is called bijective or a 1-1 correspondence or a 1-to-1 correspondence if it is both 1-1 and onto. Okay. Now, based on all these definitions, let us go through these. These are examples after all, right? These examples one by one, and let us see which one is which. Is this 1-to-1? Yes, 1-to-1. This is not 1-to-1. This is many-to-1. This is also not 1-to-1. This is 1-to-1 because distinct elements in X, in the first set has distinct images. Two different elements or more than one element does not have the same image. So this is 1-to-1. What about onto-ness? This one obviously is not onto, because every element in the second set is not the image of some element in the first set. E and F are not images of anything from X1. Similarly here, A, E and F are not images of anything from X1 under the function. So this is not onto, this is not onto. This is onto. This is also onto. Let me draw your attention to one more thing. When you check the condition for onto-ness, what will you do? You will take any element in the second set and see if it is the image of some element from the first set. Now, as far as the existence of an element in the first set is concerned, which will give us that element, A and B are of the same nature because each one of them is coming as an output from at least one input. However, you see that A has two inputs corresponding to it. That has nothing to do with onto-ness. Okay. The fact that there is at least one input from which A is coming as an output is enough for one onto-ness. Okay. So this one is onto, this one is also onto. But now, which one of these is or are bijective functions? This is not bijective. It is 1-to-1 but not onto. This is also not bijective. Actually, it is neither 1-to-1 nor onto. It does not have any of these two qualities. It fails to be 1-to-1 here because of this, and it fails to also be onto because there are soldiers surviving. This one is not 1-to-1 but onto. Not 1-to-1 because of this, but onto because no one is surviving. This, however, is a bijective function or a bijection. Bijective is adjective, bijection is noun. Not only is this 1-to-1 because we do not have this type of behavior, but it's onto as well. No one is surviving. Every element in the second set is the image of something in the first set under the function. Why did I say just now that this type of functions is very important in mathematics? You may notice one thing. F1, the function F1 that you see here, is 1 to 1 but not onto. Okay, is it possible to have any onto function that will map x1 to x2? A moment of reflection will show you no. Why? Well, because what will you do in order to cover, in order to attack all the soldiers on that side? At least one soldier on this side has to simultaneously attack more than one soldier, because the soldiers on that side are more in number. But the moment that requirement is there, it is no longer a function, because a function cannot map one input to more than one output. So if we are sticking to the fact that we are only talking about functions, you cannot have any onto, not only that the function f1 is not onto, but it is impossible to think of an onto function from x1 to x2. Same is the case here. You may think that, okay, let me just assign different targets to the soldiers 1 and 2, because here they are both attacking B. Let me tell 1 to attack A, so that way at least A is also being attacked. But then E and F are surviving. Same problem here. If you rearrange things, if you reassign their duties, still you cannot find an onto function from x1 to x2, simply because there are more soldiers here. Here we have a different type of problem. Here there is no problem with having ontoness. Ontoness is already there. Everyone is perishing. But here we have an overabundance of soldiers on the attacking side. If no one has to sit idle, then everyone has to attack someone, but because there are more soldiers here, you are bound to have a situation where more than one soldier is attacking a single target. So having a 1 to 1 function from x1 to x3 is impossible, because here the number is less. But here the only one among these four, which is a bijective function, both sides have the same number of soldiers. 4 here, 4 here. The existence of a function which is bijective and the two sets between which we have the function having the same number of elements, there is a connection between these two. And this connection, right now of course there is no need to think about these things, but I am just simply telling you some things that you may encounter in future if you want to learn higher mathematics. This fact that existence of one-to-one and onto function between two sets can be used to give a meaning to different sizes of infinities. I won't say anything more than this on this matter. Okay, and after this, of course, there are many other examples, not only these 4, of course, which we will study in the next video, next week. So see you next week with those things. Until then, this is me, Lucifer from a mathematical room. Have a nice day.